Okay, hello everyone, and welcome to recitation number 7. It's a really good one. It's gonna be all about complexity, algorithms. Like if you're ever gonna take an actual CMPS course where you have to do some programming, this is gonna be really good for you. So to start off, we're gonna spend a good chunk on trying to understand complexity. So from this graph, you can see some of the things that are usually common: 2 power n, n squared, n log n, and the graph doesn't really necessarily show how they actually grow, but it's just like in relation with each other. Like n factorial amongst what you see is going to be the slowest because it grows the fastest. You have O of 1, it's like instantaneous, just one statement. O of log n is something really nice we're going to talk about. So let's start off with actually O of n, which is this. If you have a single for loop, so a for loop is you start with an initializer. Like, hey, we say let I equals 1. Then we have our condition. So we will keep doing this for loop. It's a loop, we'll keep doing it while I is less than or equal to n. Finally, I++, it's incrementing. Like at the end of the for loop, we increase I by 1 every time. Then we go back to the start of the loop. So so this is how it would be. So I would be 1, 2, 3, 4. Every time it's getting increased by 1 until I reach n. When I reach n, since I have less than or equal, I'll also do it. But like the next iteration, it doesn't happen. I becomes n plus 1. My condition is false. I stop. So if n was like the number of students in the class, this for loop is like if I want to count every one of you one by one. So I go 1, 2, 3. Okay, so if this is our classroom, you're all here. This for loop is like, hey, I'm going to count you guys one by one. So 1, 2, 3, 4, 5, and so on. Depending on how many students we have, so like how n grows, that's how many steps it's going to take me. So we say complexity of n, O of n. Depending on how what n is, I'm going to require that many steps. So we'll start drawing this on our own to compare just a few algorithms. So this is like O of n. You keep growing. What about this idea? So now I'm going to be incrementing 2 by 2. So I is 1, then 3, 5, 7. So there's kind of a gap. Like I'm no longer doing the evens, if you'd like. So this is like if I'm counting you 2 by 2. Like I'm fast, I can recognize couples. So I break you down into couples, and I start counting 2 by 2. So 1, 2, and so on. It'll be twice as fast in theory, right? Because it's going to take me half as many steps to count everyone in the class if I'm counting you 2 by 2s. So we say O of n over 2, right? N is the number of students. I divide by 2. It's going to take me that many steps. So in the graph, yeah, we can see n is slightly slower. It grows faster, which means it's slower in terms of complexity. But you have to imagine like n is gonna be something really, really large, like so big. I don't want to say we're tending to infinity, but it's kind of like that. It's growing so big that eventually these two lines are sort of gonna meet together. Like it's not that much of a difference. If you have 9 many steps to do, and you divide it just by 2 once, okay, it's half the steps, but it's still a lot of steps. Which is why we say that O of n over 2, it's roughly the same complexity as O of n. So O of n over 2, it's the same complexity. Since we're dividing by a constant, it's not like we're dividing by some other variable, it's just a constant. And same if you're like dividing by 4, by 16, as long as it's a constant, eventually when n grows large enough, they're gonna meet. They're gonna be roughly the same as just O of n. But what's something that's faster and that eventually it's gonna not grow as fast? Not grow as fast, so it's faster in complexity. O of log n. This is a really, really nice complexity because you can do some cool things with it. But first of all, where does this complexity come from? Where does log n come from? Well, start from I is 1, my initializer, my condition. But now I'm not incrementing by 2. Every time I am multiplying by 2. So I'm just going to bring it up. So let's see what happens now. I is 1, 2, 4, 8. Multiply 8 by 2, you get 16. Multiply that by 2, 32. The gaps are going to be way, way bigger with each incrementation, which is why it's so faster. Like there's a lot of points that we're not skipping. Like imagine from 16 to 32, how many iterations you skipped. Then from 32 to 64, when you multiply again, how many iterations you skipped. It's like we're nitpicking what we want. So if this is my I, and every time I multiply 2, 2, 2, 2, 2, until I break my condition. So until this becomes larger than n, I'll keep doing it. So when do I stop? Let's count how many 2's I have. So let's say it's x, 2 power x. I'll keep doing this until like 2 power x becomes n. That's when your condition is over. Okay, well, if you do ln on both sides, so 2 power x equals ln n, so sort of like logarithmic. Well, there's a rule that says, hey, we can put the power down. So x ln 2 equals ln n. Finally, now x equals ln n over ln 2. And that's just saying log of n base 2. We'll talk about the bases in a second. But that's sort of like where the mathematical log comes from. So you no longer get confused by it. Let's see an example. So if n was 64, if I was counting you guys 1, 1, 1, 2, 3, 4, 5, it'll take me 64 times. If I'm counting you 2 by 2, okay, 32 times. But if I'm doing this sort of algorithm, for n is 64, it's going to take me around 6 steps. Because 2 power 6 is 64. Okay, what if I wanted to count everybody on Earth? So let's say we have 8 billion people on Earth, and I wanted to count everyone using some special algorithm. It's gonna take roughly about 32 steps using this algorithm. Imagine imagine you want to count everybody on Earth using O of n. It's gonna take you forever. Like try to count to 8 billion right now. It takes you forever. But with this algorithm, you only need 32 iterations. 32 steps is enough. Why? Let's see if we can actually come up with an idea. I do have something in mind. Let me talk about it. So again, we have 8 billion people. Let's say we were able to put them all in one room. Like this is gonna need a lot of cooperation from everyone on Earth. So let's say we were able to put them all in a room, and we give each person, like we tell them, hey, in your mind, take a mental note of 1. Like you count yourself. Hey, how many people am I? I'm just one person. 1, 1, 1, and so on. We have to come up with an algorithm that, with each iteration, like half the people are gone. Well, let's just have every couple look at each other. So right now, everybody's standing up. Whoop. Oh crap, it's gone. My bad. So, where are you? So we said this guy has 1 and this guy has 1. So they communicate with each other, hey, I'm gonna stay standing up and you sit down and I'll represent both of us now. So this is 1, this is 1. He becomes 2. And the other guy just sits down. So if everybody does that, imagine everybody broke down into couples of 2. And one of them sat down and the other dude now represents them. With just 1 iteration, we went from 8 billion down to 4. Because half the people sat down and everyone else now just has the symbol 2. Like now, right now, I'm 2 people. Okay. And then they do that again. So now there's another person with 2. Now these guys talk. One of them sits down. The other becomes 4. We went to 2 billion. If you keep doing that, eventually, you're going to go down so fast. Like in 4 steps, we went from 8 billion to 1 billion. Then you keep going, 5 mil. Eventually, after, let's say, 32 steps, you're going to reach just 1 person that's counted everyone. He's going to be the only person standing up and everybody else sat down. So that's a way to count everyone on Earth. And the cool thing about this algorithm, if our population literally doubles, like right now we're 8 billion. If we suddenly become 16 billion, it's only going to take 1 extra step to go from 16 back to 8, back to the normal way. So yeah, log is very cool. Moving on. So what we just did was sort of the opposite. So here we were like multiplying by 2, whereas with the idea I just described, it's like we're dividing by 2. So we started with 8 bil, and we kept dividing by 2. Same idea, but the initializing and the condition sort of flip their values. What about this? What about if we multiply by 3 each time? Well, that's just log base 3 of n. So these were base 2. This is base 3. If you multiply by 4, that's base 4. If you multiply by 10, that's base 10. So yeah, logarithms can have different bases. That's fine. But which one is faster? What can we like say they're all the same? Well, this is a formula to change the base of the logarithm. So let's say I have log base 2 of 40. If I want to change it to base 10, I'd say log base 10 over base 10. So my previous base is now going to be here. So I write 2. Whatever was inside my log is here. So I write here 40. So if you want to change it to base 10, you do this, you crisscross, you get what log 10 of 40 is. Okay, let's use that with what we just saw. Log base 3 of n. So this is when we're multiplying by 3 instead of 2. How can we relate it? Well, I want to relate it with like the normal log. The normal log is usually just base 10. So log x goes up, n divided by 3 goes down, log 3. That's the relation. But I care about the complexity. And it's going to be the same because it's the same, like they're equivalent. So the complexity of this is going to equal the complexity of this. Cool. But remember when we said, hey, O of n over 2, it's just O of n. Why? Because we were dividing by a constant. So here, log n, we're just dividing it by log 3, and this is just a number. It's a constant. Might be even smaller than 2. So the complexity of this is roughly the same as just log n. What do I mean? Hey, all the bases are roughly the same. So if you want to use base 2, 3, 2, 9, whatever, you can boil them all down to the same complexity. Cool. That's a graph. Obviously, as the base is bigger, you'll be faster in complexity. So slower in growth, it's confusing to say. It grows slower, but it's faster in terms of complexity. Like it takes less time, real time, if you actually want to run the algorithm. Ooh, okay. Very interesting stuff. Last bit of explaining before we actually start solving. Just some notations. O means less than. Omega means greater than. Think this is theta, just means equality. So yeah. Let's find out what's the complexity of this algorithm. Now, this is sort of like if you've heard of C or Java, it's sort of that, but it doesn't matter if you know it. Just focus on what we've been focusing on, like the loops. So just focus on this part. The braces are just where the loop starts, where it ends. So like we're saying, this second loop is inside the first one. So what's my complexity? Well, for I is 1 till I is less than n. Okay, that's just O of n. Without, like, I'm counting everybody one by one, 1, 2, 3, 4, 5. Same thing, j is 1, j is less than n, j plus plus. By the way, this just means you're incrementing by 1. Same as saying I equals I plus 1. O of n. But they're nested loops. So how do we relate them together? Well, you just multiply them. If you have a for loop, inside it there's another for loop. Whatever complexity the first is and the second is, just multiply them together. So it's going to be O of n squared. So O of n, O of n, n squared. Like you can imagine, when I is 1, we enter this loop. And this loop is going to run from j is 1, 2, 3, till we reach n. That's just when I is 1. Like imagine these are couples. So when I is 1, j is 1. When I is 1, j is 2, the list. Now, when I is 2, same thing for j. So 2, 1, 2, 2, and so on. You get roughly n squared. You get n times n couples. I'm going to take a break from talking. You try to solve this. If anybody is confused or you have a question, let me know. Again, don't care about the small stuff, just care about the loops. Okay. Did anybody get anything? An idea? Okay, well, as you can see, they're all nested. So like we just said before, you just have to find the complexity of each one of these loops and just multiply them together. Hmm. So can anybody tell me like the first loop, what's the complexity of it? Fair enough. So we're starting from n over 2. So I starts from n over 2. We keep going until I reaches n. So whatever n is, it's like we're starting in the middle. This is similar to doing the I equals I plus 2. Like it's similar to skipping the steps by doing this. Because we're only like doing half of them since we started from n over 2. So you can say that this is just O of n. Since we agreed, hey, O of n over 2 is just O of n. What about the second one? So it's just log of n. Since that's like the formula. So whenever your step is multiplying by 2 every time, that's just log of n. And same thing for the last one, it's O of log n. So like if you say 2 times j, or you multiply k then 2, it's the same thing. Like just, we know that multiplication is commutative. So n, log n, they're nested within each other, so you just multiply them all together. So n times log of n squared. It would have been different if these two loops were on the same level. So what we had was 4, 4, then 4. So like this was inside this and this was inside this. That's why we multiplied all three of them. If it was like this, so 4, then 4, 4, it's different because like this is inside the first loop and the second one is also inside it in terms of, let's say, hierarchy. So what would you do is the complexity of the first, this is the second, third, it's just going to be C1 into C2 plus C3. So since they're on the same level, you just add them. It's sort of like if you have for I till n, and then, hey, for j till n, but they're not nested. So this happens, it's O of n. Then this happens, it's O of n. So the whole thing is just 2 times O of n, which is roughly O of n. Because, hey, if n over 2 is going to be roughly n, then so is 2 times n roughly going to be n. What about this one? Similar, like the first two loops are similar. This is O of n. This is O of log n. Nothing changed here. Only difference was the second one in the condition. Take a minute. So yeah, it's very similar to the first loop in terms of complexity. So the first loop, what did we say? I starts from n over 2, keep going till you reach I is n. This is saying, hey, no, start j from 1, but keep going till j plus n over 2 is less than or equal to n. Like it's the same thing. Like same thing, it's in terms of number of steps. What actually happens is probably different. Like if you want to print the values on the screen, here you're going to print n over 2, n over 2 plus 1, and so on. Whereas here you're going to be printing 1, 2, 3, till you reach n over 2. So different printing, if that's what you're doing, but same number of steps. So n log n. So n squared log n. Okay. So in terms of the two complexities that we just saw, which one grows faster? So if we break them down, so like n times log n, then you have the extra n, again n log n, times log n. We broke them down like this to see that the only difference is this is getting multiplied by n, whereas this is getting multiplied by log n. So which grows faster? Or in other words, which one is slower? Well, since you're really just comparing n with log n, and we just really talked a lot about why we love log n, it's going to be faster. Faster in terms of time. We really have to be careful what we're saying. So O of n grows faster than log n. So the whole thing grows faster than this. So it grows faster, but it's slower. Like, what do I mean by grow faster? If you plug in here some value for n, you're gonna get a number that's bigger than if you plug it same number here. But assume that number is like the time in seconds for how long your program is gonna run. Ideally, you'd like the number of seconds to be lower. Isn't this due to n being greater than log n? And log n is always less than 1. Well, yeah, n is greater than log n, but log n doesn't have to be always less than 1. But it's just simply just because of this, exactly. O of n is bigger than log n, so it's faster, but at the same time it's slower. You get it. Next idea. We have 2 more of these, and then we'll go into algorithms. Let's actually do this one together, and then you'll do the last one on your own. So first loop, it's just O of n. Like some of these things that you just have to gonna be like instinct, like right away. I'm looping from 0 to n, that's just O of 1, and move on. Be confident like that. The other one is, hey, J0, J is less than I. Well, this is a new. This is a new. Like we're relating J to I. J isn't dependent on n, it's dependent on I. So how does that work? Well, like we said, the first loop is gonna go O of n times. Fair enough. The second is gonna go O of I times. But what does that mean? Like I changes with every iteration. It goes from 0 to n. What does that mean? Well, let's see some examples. When so I takes the values 0, 1, 2, blah, blah, blah. What does j take depending on I? Well, if I is 0, so j will keep going until it's strictly less than 0. Like that's the condition. But j starts from 0. So right away, you don't even enter the loop because is 0 strictly less than 0? No. 5 is not strictly less than 5. It's less than or equal, but not strictly. So right away from this part, I'm getting any iteration. What about from 1? So j is 1. Sorry, I is 1. J starts from 0. You only get 1 iteration. Let's see. Yeah. So you only get 1 iteration. That's weird. Let's take a moment to analyze this. Oh, yeah. So yeah, it run 1 time. So j is going to take the value 0. It's like it's running once. When I is 2, j is going to take 0, then 1, then the condition breaks. So it's like it prints, like when are we printing? That's another way of asking it. For what values of j are we printing this star? Well, when j is 0 and I is 1, we print. When j is 0 or 1 and I is 2, we print, and so on. So when I becomes 3, if j is 0, 1, 2, we print. When j is 3, we don't print because the condition is now false. 3 is not strictly less than 3. Okay, good. So what's the total print operations? It's going to be 1 plus 2 plus 3 plus 4, so on. Right? Like depending on what the value of I is, that's how many times we print. When I is 1, we print once. When I is 2, we print twice, and so on. Sort of like you're summing from 1 to n, I. N into n plus 1 over 2, that's just O of n squared. So the complexity is O of n squared. That's the really mathematical proof. Another way of seeing this is just what's the worst possible value for I? When you're calculating the complexity, you always assume the worst case scenario. So I goes from 0 to n. The worst case for I is it's going to be n. So it's sort of like you're doing O of n squared. Like this would be acceptable as a proof if we're not asking for a lot of details. Last one before we move on to algorithms. Try to figure this out. Again, I don't care about this. And use the idea of worst case scenario. Like what's the worst value for I? What's the worst value for j? This is just saying modulo. So when j is divisible by I, we'll enter this loop. So what's the worst case scenario? Assume j is always divisible by I, so you always enter the loop. Okay? Take a minute to do this. So, first loop. Surprisingly, it's just O of n. Second loop. Worst case scenario for I is that it's going to be n. So n times n, that's O of n squared. You're looping from 0 until, in the worst case scenario, n squared. So that's O of n squared. Assume you always enter the if statement. So you're always doing this loop. Well, you loop from k till j. What's the worst possibility for j? So what's the complexity? It's the same thing, n squared. And since they're all nested together, you multiply them, you're going to get O of n, 5. All right. So what's the worst case for I? It's n squared. What's the worst case for j? It's n squared. That's why we get that. And you assume always that I divides j. Unless like there's a special variable here that never divides it, like unless you know that you never enter the if, you're gonna assume that you always enter it. So these are some of the examples, like what happens. When I is 0, nothing happens. When I is 1, j becomes 0. So when I is 1, j is 0. We enter the if, but j is 0, so you never print anything here. When I is 2, you're going to go till 4. When is 4 divisible by... when is j divisible by 2? Since I is 2? Well, only when it's 2, right? Like these are the values that j is going to take. But for what values does it actually divide I? Well, for the 0, the 2. When we reach the greens, what are the greens saying? Hey, let I be 3. So j is going to start from 0 and keep going till I times I, which is 9. So j is going to take all these green values. When does j divide 3? Or when is 3 divisible by j? When is, j divisible by 3? Well, when j is 3 or when j is 6. So it sort of seems like there are not a lot of operations. Like we just said n power 5. That's a lot. But it seems like, I don't want to say we're nitpicking, but it's not similar to the log, but it's sort of like we're not choosing a lot of values in this scenario. In the next one, you choose only 4, 8, and 12. It is a lot because, hey, you're saying, okay, 8 is divisible by 4 in this case, so you're going to print it 8 times. Then you're going to print it 12 times. So when I was only 4, you printed 25 times. Every time you're going to be printing more and more and more. Like you have to assume that n is going to be so big that you're eventually going to be overwhelmed by the amount of printing that you're doing. Actually, this is the last question before we dive into algorithms. So they're asking, is this O of n cubed or not? Like you're summing n squared, or from 1 squared all the way till n squared. Is this less than O of n cubed? Like is all of it as of complexity? Is it less than that? 2 ways to do it. Well, this is a geometric series, so you can either find out the closed form, which is going to be something like this. Don't know the exact form, divided by something. and all these somethings are constants, so you're going to get that yes. Or another way is, hey, well, I know that 1 squared is definitely going to be less than, oh, sorry, this is n squared. 1 squared is going to be definitely less than n squared. 2 squared is going to be definitely less than n squared. Da, 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 da. How many n squareds do you have? Well, at most you're going to have n minus 1 plus 1, which is n. So it's like n times n squared, which is n cubed. Yes, it is O of n cubed. You didn't get that a lot. It's okay, you can work on it on your own time. Because now we have to move to the last idea, which is algorithms. Hopefully you took in class binary search and sorting. They're really important, especially binary search, because the complexity of this is log n. Why is it log n? Well, just think of the examples that you might use binary search. Binary search requires you to have a certain condition. Like if I give you a bunch of numbers, 1, 10, 73, 100, and so on, it gives you, like I'm going to give you this guarantee, like the numbers I give you are in ascending order. So having that sort of information, like it's already sorted in ascending order, it allows you to use binary search. And binary search is all about, hey, every time I cut my values in half. Like if I'm looking for a certain number, like let's say I want to look for 99. I have these 5 numbers, I'm looking for 99. Well, cut it in half. What's the middle value? It's 73. Is 73 smaller or bigger than 99? It's smaller. So like you cut off this part, you don't care about it anymore. Now you're focusing on just this part. You cut in half, you find 99. It might take more steps, but that's the idea. Every time you're cutting in half, just like when we were counting everybody on Earth. Sorting, hey, you have it unsorted, you want to sort. A lot of cool methods here, like bubble sort, merge sort even, that's kind of complicated. Read a lot about them, and you can see in the assignment if you're going to need them or not. I'm going to do a couple of examples on algorithms. Like you can actually try to write them, but for now, since this is maybe the first time you're seeing them, it's okay if you just like write in English words, what are you trying to say? Like you don't have to write quote unquote code right now. So I'm gonna do this first one. Then I think there might be 2 or 3, maybe 2 other examples that you can work on. If you need to leave at any point, please feel free to do so. Given n integers, such that each value is between 1 and 1 million, your problem is to find the min, max, average of these values. You're also required to print the values sorted in increasing order. Okay? Well, when you want to find an algorithm for something, you have to break it down to small steps. Like they're asking for a lot of stuff. Min, max, average, sorting. So break it down. Like let's say we want to find the minimum first. So what would be my algorithm? I say, hey, loop over the integers given. So you're given n integers, right? So loop over the n integers given. Okay, I want to find minimum. So let's say we start off minimum with minus infinity. That's fair, right? Oh no, I actually started with plus infinity. Like you want to find the minimum, so just put the biggest number you can think of in minimum. 99999, so on. Well, whenever I find something smaller than my minimum, that's going to be my new minimum. So I'm looping over each integer. If this integer is smaller than my minimum, well, hey, minimum now equals this integer, okay, inside my loop. And this is inside my if. Well, I can do the same thing for the max, right? I don't have to. I could either two things. I could either make another loop where I try to find the max, but I can make use of this same loop, right? I'm already looping over all the integers. I'll try to find the max as well. So max equals minus infinity. I want to find the biggest number, so I'll start it with the smallest value possible. If this integer, because remember, we are looping over the integers. So at each iteration, I'm grabbing them. So if I have 9, 8, minus 5, their values is between 1 and 1 million, plus 5. This thing. So first of all, you grab this. Is it smaller than plus infinity? Yes. So min is now going to be 9. Then you grab this. Is it smaller? Yes. Min is going to be 8. Then this guy's turn. 5. Is this smaller? No. You're done. The minimum is 5. You found it. Same thing for the max. If it's bigger than the max, then it's going to be my new maximum. Equals this integer. Okay, we found the min, we found the max. We still want to find the average. Why not use the same loop again? How do you find the average? Like, these are simple everyday questions. If you want to find the average of a bunch of numbers, you sum them up, then you divide them by how many integers you have. So sum equals 0 every time. So this is also in my loop. Now every time, just add your integer to your sum. That's fair enough. It's also on the same level of this loop, this for loop, if you will. So you're summing. When should you divide? When you finish the loop. So when you finish looping over all the elements, so let's say right now I'm back here, that's when I say, hey, average equals sum over n. So we were able to find the minimum, maximum, average, and even, hey, the sum, if they'd like it, in one loop. That's good. The last part, you are required to print the values in sorted increasing order. You've taken a bunch of sorting algorithms. So you can pick whatever one you want. But there's a reason like why we said the values are between 1 and 1 million. That's sort of useful information. On your own time, search what an array is. So this is like now it's just programming, actual programming. Search what an array is. You can think of it as just like a bunch of boxes next to each other. So right now, when I created min, max, sum, it was like just a bunch of floating boxes. Min, max, sum, and average. And eventually I had my values here that I wanted. So min was 5, max was, let's say, 10,000. And whatever sum and average are. But the fact that they told us that the values are between 1 and 1 million, it gives an intriguing idea for how we can solve the sorting, which I'm not going to talk about right now, because it requires some personal effort from you. So if you'd like to figure out a new idea of how we can do the sorting, search what an array is, learn it, and then talk to me, or maybe I'll mention it on Monday's session. Like, how can we use the idea of an array to do sorting, given this information? Okay. So we have this question, and we have this one, and we're done. Oh, time is over. I'm just gonna solve them. But I would advise that you try to think of. Actually, listen, I'm gonna give you a minute or two to try to solve this. Then I'll do it. So in this we were talking about it in recitation 5. It's just the quotients. So they're asking, find an algorithm that prints all the elements. Like, assume you are given m and n. Can you print all the possible values m over n? So, like, can you find a way? Okay, electricity went off. I'm gonna do this before I shut down. So what's this algorithm? Hey, you're given m, like, hey, I tell you m is 100 and is 50. They're positive because just print for me every possibility. So, well, what are all the possible m's? I loop from I is 1, I is less than m, I plus plus. Then I loop inside it, nested, from j is 1, like I want a different variable. J is less than n, j plus plus. Like, think you're just trying to find all the possible couples, like what we did with, what was it? I'll try to remember. So just say simply now, I'll print m over n. That's it, right? So when I starts with 1, n is going to loop over from 1 till 50. So you're going to print 1 over 1, 1 over 2 till 1 over 50. Then j becomes 2. You print 2 over 1, 2 over 2, all the way to over 50, until you reach 100 over 1, 2 till 50. There might be repetitions in terms of value, but that's okay. So those are like all the possible couples. It's just the idea here that you actually had to use 2 nested loops, which isn't easy. Last question. Given a list of n distinct integers sorted in ascending order, find the pair of values closest to the average such that one of them is just smaller, the other is just larger. Very interesting question. So you have a bunch of numbers. Let's say average is the average of these numbers. They want you would like to find 2 numbers. One is just smaller than the average, so you want just smaller, and you want just larger. Than the average. So how would you go around to doing this? I'm going to give you the hints. You can try to solve this on your own time. Well, step 1, find the average, right? If you want to find, your main problem is to find just smaller and just larger. But in order to find that, you're always comparing them with the average. So find average. Okay. Then you can do 2 things. You can either do like what we did with the plus infinity minus infinity with the min and max. If you didn't like that whole thing, you could have just said, hey, just smaller equals just larger equals first integer. Actually, forget this. Going back to the min and max, if the idea of minus infinity and plus infinity bothers you, you can just say, hey, min equals max equals the first element. And then you start looping from the second element forward. That's fine. Like you see, like instead of minus 50 plus 1, you just give it the first element and you keep concurring with the rest of the elements. I was going to say the same thing here, but it doesn't work because we want them to be just smaller than the average and just bigger than the average. So that might cause problems. It might not. Okay, so let's say you do the minus infinity plus infinity idea. Now you want to loop. Let's say I'm working with just smaller. Just if I find an integer, like this is my average, and I have something that's smaller than it. If I find something that's in between them, I want that because it's like closer to the average but smaller than it. So what does that mean? If I find an integer that's bigger than e1 or bigger than my just smaller, and it's less than my average, that's going to be my new just smaller because it's just smaller than the average. It's closer to the average and it's smaller than it, so it has priority. Do the same thing for the just larger. Like, let's say this is my just larger. I find a new element, E4. Well, E4, it's bigger than the average, and it's smaller than just larger. So I'll take that. That's your other condition. And so on. That's roughly the steps of the algorithm. You just have to either write it in better English, better paragraph, and maybe even try to write pseudocode for it. Yeah. Okay. So that's it from me today. If you have any questions, let me know. Okay. Otherwise, if you don't have anything, I'll see you next time. You're welcome. Anytime.